All right, shall we? All right, so we left in the middle of this example here, and I think we ran into a little bit of an obstacle. So what was the problem we ran into last time when we left off? Go ahead.
Zero and I change the 5 to -5 to 0, I think. Then that cancel 0.
Right. So something I admit this, I'll admit this again, that I did not warn you to watch out for is it really does benefit us to move from left to right. So let's do this. Let's try to put a 0 there, knowing that we're gonna have to deal with that again. So how could I make a 0 show up there? In fact, I'll give you the option. Should we just go back a step? Or do you want to start with? Go ahead.
Row 3 and add, or you can take 2 of row 3 plus 5 of row 1 and just get the 0 and 5 spot.
2 of row 3 plus 5 of row 1.
Yeah.
Oh, sorry. From where I am now, you mean?
Yeah.
Okay, yeah. Two of row 3 plus 5 of row 1 and put that back in row 3?
Yeah.
Okay. All right, so what is that last row going to look like now? So hopefully this first entry is a 0. I think that was the inspiration behind that calculation, right? Okay, good. So then what's the second one going to be? 2 times 0 plus 5 of -1 is -5. 2 times 3 is 6, plus 5 times -2 is -10, so -4. And then 2 times 15 is 30, plus 5 times -21, so 30 minus 105, minus 75. Double check me, but I'm pretty sure that's okay. Go ahead. Row 2. Sure did, thank you. That was 2 steps ago. Okay. Hopefully that was all. I didn't do that. I didn't use that to make any calculations, so I think I got lucky. Okay. All right, so now what should my, so I don't think let's remind ourselves. So I want to get this upper triangular form, right? I think we only have one more barrier between us and that. So what else do we need to do? Go ahead. That -5 needs to become a 0. Now, can I do that without messing up the zeros I already have? This time I can. Provided that I do what? Right, so provided I leave row 1 out, because row 2 has a 0 in that column as well. All right, so we know we're going to leave row 1 out of it. So what should I do with row 2 and row 3 to get what I want? I'm going to put something into row 3. But what do I want to put there?
Would you do -5 row 2 plus 7 row 3? Right. So I think the 5 and 7 are
those are both prime. So I think you have one of two options. Either, yeah, take a multiple of each, or leave one of the rows alone and deal with a fraction. Both are fine. But I'm going to go with what was suggested. So what was it? 5 of row 2?
I guess it would be minus.
Yeah, they're the same sign, so I got to subtract one of them. Minus 7 of row 3. Okay. So 2, -1, -2, -21. I really don't want that to be negative. All right, so no way this could have changed. This better have become a 0, otherwise I was wrong. But 5 times row 2 is -35. -7 times row 3 is +35, so I feel good about that. 5 times row 2 is 15. -7 times -4 is 28, so 43. And then, not even gonna try. 5 times 47 plus 7 times 75. Real? Oh, nope. Okay. I think that's what I got. But 43 doesn't go into 760 evenly, so I feel there's probably a mistake somewhere. If anybody sees it right off the bat, let me know. Otherwise, here's what I'd rather focus on. Are we okay with the goal of this upper triangular matrix being the thing to shoot for right now? Okay. We're kind of understanding how to get there. So let's do this. Oh, no, not that. Okay. Let's kind of reflect on the process here. So if we kind of either look at this example or one of the previous ones we did yesterday, like what's the first thing we tried to do? Or can we tell? You know, the first thing we did, yeah, we cut this row down to 1/3 of what it was. But what were we working toward? Can we tell? Go ahead.
For future reference, do you want us to raise hand or just stay?
Yeah, if I'm not looking at you, which I don't want to always be, yeah, just go ahead and shout at me.
Okay.
I'm fine.
First thing that we're trying to do is get 0 in the leftmost column.
Okay. In the second row there?
Yeah.
Okay. And even though we didn't do it in this order, I really think it's most beneficial to put a 0 there than there. So basically, the only non-zero entry I want in that first column will be at the top. And then the second row, I would like it to have a 0 in the bottom row. And once I have that, then I've kind of fulfilled the thing I was trying to do. I've got my upper triangular form. And then from there, I can kind of back substitute and solve. So one of two possibilities. There's either a mistake in here, or I just threw these numbers together without any kind of regard for if the solutions would be friendly numbers. I feel like we were all careful, and there's a lot of you watchdogging me, so I feel like we probably did it right, and the numbers are just gross. But right now we can find x sub 3, right? And I don't think this reduces, because I'm almost sure 43 is prime. So unless we approximate, that's what we got. Could we then find x2? How would we do it? So negative 7x2 plus 3 times this hideous beast equals 47. I believe wholeheartedly you could do that and then iterate it one more time to find x1. So that's essentially what the goal of that section is. If I didn't use this term yesterday, I should have, but I think I did. Gaussian elimination. So basically this is the process that turns a matrix into a reduced, or not reduced, a row echelon form of a matrix, or equivalently, an upper triangular matrix. Good so far. All right, so let's move on to section 2. We're going to expand on this idea a bit. Sure. Cancel. If I can find it. All right. So section 2, we're going to talk about a different kind of elimination, related, but called Gauss-Jordan elimination. So now let's solve one of these, but now we're going to bypass that back substitution step. So we talked about that idealized matrix, right? Like there's a version of this matrix that if I get to it, I get all my solutions for free. Where x equals a, y equals b, z equals c. What does the square part of this matrix? What does the left-hand side of this matrix look like? If it's going to give me my answers kind of plainly. Right, and everywhere else is 0. So 1, 0, 0, 0, 1, 0, 0, 0, 1. But the good news is the rationale to get here is very much, we're going to start this the same way. So for right now, let's work towards getting our upper triangular matrix. So let's write this as such: 1 minus 1, 5, 3, 3, negative 1, 1, 3, 2, and then negative 6, 10, 5. So I'm going to say this: goal number 1 should be top left. I would love to have a 1 there. We have that, right? Okay, we can move on from there. Step 2/3 is, and it doesn't really matter which order you do these. If you get a 1 where we got it, like remember the issue we ran into last time at the very end of class? The best way to avoid that happens, to avoid that happening again, is the very next thing we should do is to take care of the rest of this column. 0 that out, 0 that out. So before we go on, are we okay with why I'm saying that's our good next step? Okay. So if we work from left to right, then we're going to avoid that kind of whack-a-mole. Does that game still exist anymore? Or am I just 1,000 years old? Whatever. We're going to avoid having to solve a problem we've already solved. Okay, so we got the first job's done. How do I make zeros happen where I want them to happen? I see at least 2 good options. What do you got? Row 3 minus row 1? And put that where? Okay. I believe strongly that would put a 0 in that first entry of row 3. So 1, negative 1, 5, negative 6, 3, 3, negative 1, 10. All right, and then this last row 3 minus row 1. 1 minus 1 is 0. 3 minus negative 1 is 4. 2 minus 5 is negative 3. 5 minus negative 6 is 11. Okay, bullet number 3 down here is done. Go ahead. We sure can, but why? Okay. Row 2, row 3, you said? Okay. So row 2, row 3. I'm going to admit that I don't fully see what you see yet, but I know that this is legal. So if we do everything right, we're going to be fine. Okay, so we got to swap. So we have not done 3, we have done 2. Okay, what's a good next move from here? Row 3, -3, row 1. I assume put that back to row 3. Cool. All right, 3 minus 3 times 1 is 0. 3 minus 3 times -1 is 6. -1 minus 3 times 5 is -16. And 10 minus 3 times -6 is 28. Please double check me on these. I'm going through them pretty fast. And like we talked about like I mentioned last time, none of the individual operations we're ever going to do like in this process are hard. But if I do it 30 times, I might miss. Did I miss? Negative where? Row 3 minus 3 of this. Okay, I feel good about 28 though. Row -1 minus 3 times 5. Okay. Okay, if there are mistakes in there, I'm not seeing them yet right now. Okay, column 1 looks fine. 1, 0, 0 down the left-hand column. Now, our next job is not necessarily to go, left from the left to right, top to bottom. When we move into a new column, I think our next goal should be to put a 1 basically in whichever row we need to put it in. That'll be dictated by which column you're in. So now I would like to have a 1 in the center of this matrix. Many ways I can see to make that happen. I'll let you throw one at me. Go ahead.
Guess I would. Two.
Row 2 from row 3. Okay. And then put that where? Okay. Row 3 minus row 2. Back to row 2. All right. So what did that do? This better not have changed. 6 minus 4, 2. -16 minus -3, -13. 28 minus 11 is 17. Okay. I agree. Now what? I'm getting the sense that we're kind of fraction averse. I'm gonna ask us to embrace them. Because if we embrace them, this process of putting a 1 where you want it becomes much simpler. Is that
Could do R2 plus 3R1.
row 2 plus 3R1? I could, but what's the issue if I involve row 1 now? This 0 goes away. So now we're like, hopefully it's kind of good news that after we've like set column 1, we basically want to leave row 1 alone. Otherwise, we're going to reintroduce non-zero quantities.
Because you were saying fractions.
Yeah.
You do 1/3 times row 3.
1/3 of row 3?
Yeah.
And do what with that? Like just put it back where it is?
Well, yeah.
Okay. You could, that would put a 2 here. -16/3 is 28/3, right? Which is fine. But let's think about what our goals are. We want a 1 right in the middle of this matrix, right? Go ahead. What, I might have lost you. Say it again.
Take row 2 divided by a third of row 3 and put that in row 2.
I don't think so. It sounds like you're saying to do something with this row and then just put it here.
I'm saying that if we divide, so he said to like take a third of the row, and get to the 2. I'm saying if we took row 2 and divide it by the third, you would stop there and just put that back in the row 2.
What would that make this row?
Row 3 would stay the same, and then the 2 because you got the 2. You take
Okay, yeah, I don't know if I'm following. I'm not sure that it's legal. But even if it is legal, I think there's something we could do that would be a little much more efficient. Go ahead.
Say like a half or like 1/2 times row 3, make that 6/3, and then you could say like that, or yeah, 1/2 times row 3 minus row 2, and then put that in row 2. Make that 1.
That would absolutely work. I'm looking for something even simpler. Go ahead.
We just divide row 2 by 1/2, or I mean divide by 2.
Absolutely. Right. So even though that might not be our first choice, I want to at least put it out there that this is, it probably doesn't give you the friendliest numbers, but I'm pretty sure it's the most straightforward way to accomplish our next goal. So 1/2 of row 2 goes back to row 2. And I will unfortunately kind of tell you now, if there's probably not a way to get through one of these without fractions showing up at some point. Okay, now I think I've done what I want. So I've got the 1 in the middle. So I've got the 1 in column 2 where I want it, right? But now my next goal, this is where we're going to start to deviate from the upper triangular matrix a little bit. Because if I wanted to make an upper triangular matrix, I would 0 this out and then we'd be done, right? But now I want to 0 this out and 0 this out. So in any order, let's do that. How would I get a 0 somewhere? Go ahead.
If you subtract 6R2 from row 3.
Okay.
And replace row 3 with that.
Row 3 minus 6R2 goes to row 3. Okay, here's where we need some courage. That shouldn't change. This should be a 0. -16 plus 39, essentially, I think. Because I think -13/2 times 6 is the same as 13 times 3. So 39 minus 16. And then 28 minus 51. Oh, that feels good. All right. Any questions about that step? What's a good next step? Go ahead. Yeah. So, yeah, we got a little bit fortunate there because that's a pretty straight elimination. Row 2 plus row 1, back to that row. Five minus 13/2 minus 3/2. And then 5/2. All right. Column 2 looks great. Go ahead. I would love to. In fact, I'm going to condense into the last step. Just last step we just did. 1/23 of row 3. So we've put all the ones in this matrix where I want them. I feel like I know that z is equal to -1. All right, now what? I think I'm 2 moves away, and I'm probably going to have to do them at the same time because I write too large. What's next? What should my next goal be? Right. Cool. That's a good one. What will turn the -3/2 into a 0? Let me rephrase that. What will turn the -3/2 into a 0 without messing up any of the other work I've done? At this point, there's your options are very limited, which is hopefully good news. So as we move from left to right, so let's kind of go back a little bit. So after we finish this row, or this column, I mean, did we ever do anything with row 1 again? I don't see R1 anywhere. I have to take it back here. I did, but I altered row 1, but I didn't use row 1 to alter anything else. Why didn't we? Because I think we were actively avoiding it. Why didn't I want to use row 1 and add it to something else? What was the danger? Right. So now that I have the first 2 columns settled, I basically don't want to use row 1 or row 2. to make those modifications. Like I can use them to add, but I don't want to, like if I add row 1 and row 3, I don't want to put that back in row 3. Because I don't want to put it back in row 1.
By 3/2 and then.
Let's see. 3/2 row 3. I think you did say that the first time. Plus row 1. And I'm running out of space. Let's do both things we need to do at the same time. What's the other thing we need to do to handle row 2? 13/2 row 3 plus row 2. That goes to row 2. Okay, so bottom row is perfect. Top row, the top row, there's no chance the first 2 entries are going to change. What better have happened to this negative 3/2? That better have happened. All right, 3/2 of negative 1 plus 5/2. I think that's 1. 0, 1. 13/2 minus 13/2 is 0. 13/2, sorry, negative 13/2 plus 17/2 is 4/2. All right, I think we win. So what's our solution here? 1 to negative 1. How are we doing? Any questions here? So a couple things I want to ask about. I mean, like now that since I've written down like all the operations we did, you know, I believe strongly you could all like recreate these if I gave you, all right, do row 2, swap row 2 and row 3. What's the matrix going to look like? The thing I'm more focused on is, could you decide these steps on your own? Like, could you kind of drive this process by yourself, which I'm sort of forcing you to do. But the rationale is kind of what I'm looking at. I don't know if we need to do another one just white yet. So let me ask you a question. So if I have a system of a bunch of linear equations, how many solutions could it have? We've seen some possibilities. So we just looked at one system of equations. How many solutions did this have? It's really not 3 solutions. It's one solution that contains 3 corresponding coordinates, right? So it could have one solution. Do all systems of equations have one solution? What are some other possibilities? Go ahead. They have infinitely many. Infinite solutions. What else? 0. They don't have any kind of solutions. Notice I didn't ask you how many equations. I just said a system of some equations. Does that change your answer if I change the number of equations? It shouldn't. So these are the only, so as long as my equations are linear, which if we're using matrices to talk about them, those are the kinds of equations we're inherently talking about. These are your 3 possibilities. I have one solution, I have infinitely many, or I have none at all. So now having done that, can we like distinguish between those cases? So let's go back to this one here. Let's start solving this. So 1, negative 2, 3, 1. All right, what would we like to do first? Yes.
I would
Okay. How come? Okay. Wait, row 2 plus row 3? Okay. All right. So you're making some zeros up here. Zero, zero, 3, 5. Okay. In general, I mean, it's hard to generalize things. We've only done one of these, like, all the way to that identity matrix. But what was the first thing we tried to do with the last problem? Get a 1 there. So got it for free. So beyond that, after you get the 1 there, what would you like to do next? Which we essentially just did. Zero's below it. We got a 0 to the right of it, kind of for free. But our next goal right after that should be to get zeros below it. So because of that, what's another good move to do?
Could you, divide the first?
I could. Let's do that. So 1/3 row 3, back to row 3, 1, 5/3. Go ahead. Row 2 is all even numbers, so yeah, let's do it. Let's tack all these on there. Wait. I don't think I've violated anything. I think I'm okay. All right. 1, -2, 1, 1. All right. So scaled rows 2 and 3 to, well, let's ask, why did we scale row 2 that way? Okay. Okay, so we're planning for the future. Why did we scale row 3 the way we did? Because 0, 0, 1 is desirable. We know we want that at some point. Okay, good. So related, but slightly different reasons for doing both those things. What should we do next? I'm going to caution against that because I think that would hurt us later. Why am I saying that would hurt us? So if you divide this middle row by -2, you're going to have a 1 here, right? -1/2, -1/2, -1/2. I think this is going to be a problem because that's going to cause some of our zeros to go back to non-zero.
I don't think it's a problem.
We'll get there. That's the point. So what's a good move to go from here?
Row 2 minus row 1.
Row 2 minus row 1. Back to where?
Row 2.
Row 2. Zero, zero, -2, 0. 0, 0, 1, 5/3. Starting to feel weird about it. Okay, what now?
You have to stop there,
Why? Why would I have to?
because it's saying Z has. So for Z has that, so they have two Z.
Let's do this first. Let's say that now I think it's okay to divide that row by -2. So -1/2 row 2, back to row 2. I think now we can say that this is impossible. Is there a world in which we can get that -2 to turn into a 0? Without, how would you add 2 to it? We can't add like, the only thing we're allowed to do is add like rows to other rows. I can't just add like a 2 to that entry. And since there's only zeros below it, I don't think there's any way to make that anything else. So someone's saying this thing has no solutions. Is that true? So the bottom 2 rows of this matrix tell me z equals 0 and z equals 5/3. Is it possible for z to be both those things? No. Let's do one more thing to drive the point home even further. This can't happen. Let's do row 2 minus row 3 and put that back in row 3. What would that do? 0, 0, 0, minus 5/3. So what does that bottom row say now? That's absolute nonsense. So this matrix represents an impossibility. I think it's deeply not obvious here that that's true. So we had to do some reduction to get there. But yeah, once you can convince yourself or me that you have no solutions, yeah, we can get out of there. How we doing? All right. So you can probably guess what I'm going to throw at you now. All right. So let's handle this. All right. What should we do first? Or what's the first thing we should try to do? Get a 1 in top left corner. How can we do that? Row 1 minus row 3. Okay. Hold that thought. Yeah, you might be onto something. That might be a red flag that this can't be solved in the way you're thinking, but let's make sure we can prove that. So row 1 minus row 3 would give us 1, 2, -4, 0. Okay, what's our next job? Get zeros under it. Cool. How? Go ahead. Okay. Let's handle row 2 at the same time. What should I put back in row 2? For row 3. Oh, sure. Yeah, okay. So top 2 rows are going to be the same. Row 3 minus row 1, 0. Actually, I take it back. So here's something I was kind of building up to is we got from this step, we got a 1 in this entry, right? Once we have a 1 in that entry, I think we can use that 1 to zero out everything else in that column. I'm not saying that's the only way to do it, but I promise you that'll always be there. So how can I use this 1 to zero out this 4? Right, so minus 4R1 plus R2 back to R2. So that'll be a 0 minus 4 times 2 plus 2 is negative 6. 16 minus 6 is 10. Column 1 looks good. Now what? Or rather, what's our next mission? Go ahead.
By 2.
So make it all even? Yep. So 1/2 row 2, back to row 2. 1, 2, negative 4, 0. 0, negative 3, 5, 0. Anything else you notice? Similarly? Yeah, row 3 is all divisible by 3. Okay. Good. So what should our next major goal be? I want a 1 in the middle. So now that I'm in the second column, I want a 1 in the second row. Pick your favorite way to make that happen. Go ahead.
Yeah. I guess we would
4 times R3. Okay. Is that the only way to get this done? I don't know why I thought I was gonna do it up there. That's not gonna happen. Do we have any suspicion yet about how many solutions this has? Zero, 1, 1, 0. I hear a vote for infinite solutions. Why? Why do we say this? let's prove it. So I agree with you. We're almost there. We got a 1 where we want it. What's our next goal? Cool. Let's do them both at the same time. So, and I'll remind you, how do we do it with row 1? We used, once we got a 1 in the top left entry, we use that 1 to zero out everything else in this column. Now that we have a 1 where we want it in the second column, let's use it to zero out this 2 and that -1. Go ahead. That would do it.
Minus row what?
That would also do it. And again, like there are other ways to get those things done. But if you're stuck, like that approach will always be there for you. All right, so second row is the only one I left alone. 0, 1, 1, 0. Third row becomes row 2 plus row 3. 0, 0, 2, 0. First row becomes 0, 0. 6, 0. Go ahead. It's not. Thank you. 2 row 2. Oh, it should be minus though, right? Is this true? Then I'm going to ask for a small alteration to this operation here. How might I change it?
-2R2 plus R.
Yeah, basically just take the opposite. If I do that, then I'll get 1, 0, -6, 0. I don't know if I believe we're still thinking infinitely many solutions. That's what I think we're going to find. Go ahead. Yep. Something went wrong. This is supposed to have infinitely many solutions. So there's something went foul here. So look at the top 2 equations in our very original system. How are those top 2 equations related to each other? What's that? Yeah. So I don't have 3 different equations. I have 2 different ones. Those first 2 equations are essentially identical. So because of that, I should not have gotten this unique solution. So let's find the mistake. So row 1 minus row 3. 1, 2, minus 4, 0. Row 3 minus row 1. Here it is. Thankfully, it's way far back. I'm pretty sure that should be a 5. Now, if I add row 2 and row 3, get 0 and anybody seen it? I don't want to start over, but I feel like I'm going to have to. All right. It will, yeah. So negative 4R3 plus R2. Negative 4R3 plus R2.
I got negative 17.
Where? This ring. Which means row 2 plus row 3 would be negative 12/3, negative 4. All right, in the interest of time, this is happening. I'm sorry. Oh, I don't like it either. So we realize that the top two equations are basically they're absolutely multiples of each other, right? So let's do this. 1 minus 1, 1, 0. What if I do row 2 minus 2 row 1 and put that back into row 2? What's going to happen to row 2? Zero, 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 zero. I still want to have a 1 in my first column. So I'm going to swap row 1 and row 3. 1, negative 1, 1, 0. 0, 0, 0, 0. 2, 1, negative 3, 0. I would like to have a 0 where that 2 is. So I'll do row 3 minus 2R1. Zero, 3, negative 3 minus 2 minus 5, 0. All right. So what's going on with that row full of zeros? What is that going to do to us finding our solution? Good. Right. We essentially have two equations to figure out the identity of three different unknowns, which is not enough. But even though we have an infinite number of solutions, we can still say something about them. So let's keep on reducing this. In the meantime, I'm going to bury that 0 row. at the bottom. 1 minus 1, 1, 0. 0, 3, negative 5, 0, 0, 0, 0, 0. All right, so from here, what should my next goal be to do? I want a 1 in the middle still. How can I make that happen? Yeah, so remember what at this step, I think row 1, we can't put row 1 anywhere else. We just got we can do things to alter row 1, but we don't want to use row 1 to alter row 2 or row 3. Go ahead. Right, so we're gonna have to eat some fractions, but if we just let row 2 handle this, 1/3 of row 2 goes back to row 2, and I get 1, negative 1, 1, 0, 0, 1, negative 5 over 3, 0, 0, 0, 0, 0. What should my next move be? Row 2 plus row 1, and where's that going to go? Row 2 plus row 1 back to row 1. One, 0, negative 2/3, 0. All right, what now? I can't do anything else. So my next goal would be to put a 1 here, right? The only way to do that is to move one of the other rows down, which is going to undo all my work. So that idealized matrix we shoot for, it's a good thing to shoot for when you have a unique solution. Otherwise, you're never going to find it. So we have infinitely many solutions, right? But we can be more specific than that. So let's do this. What is this? Let's retranslate this top row into back into an algebraic equation. What does this top row say? X minus 2/3 z equals 0. And the next one? So here's my solution. A few different ways to write it, but basically what I've learned about my solution is this. As long as x is equal to 2/3 of z and y is equal to 5/3 of z, I'm okay. There's an infinite number of combinations that make that happen. But when we say there's an infinite number of solutions, that doesn't mean that everything is right. I'm still restricted by something. In this case, that's that restriction. So in this case, z becomes what's called a parameter. So I have an infinite number of solutions, and basically think of z as this dial. Whatever I choose for a value of z, that's going to dictate what x and y are. How are we doing? Okay. So we talked about the 3 different kinds of systems in terms of how many solutions they have, and now we've seen one of each. So the consistent system is basically everything I showed you yesterday. Those have a unique solution that we can find either through back substitution or through getting the ideal matrix that reduced row echelon form, the 1, 0, 0, and so on. An inconsistent system which has no solutions at all, and then a dependent system which has infinitely many solutions. So the one we just talked about here, all of our solutions depend on z. So everything we solve, everything we deal with here is going to have, is going to hit one of those 3 options. So now I'm showing you a matrix in row echelon form. How many solutions does this system have? Infinitely many solutions I gotta vote for. I gotta vote for no solutions. Uh-oh, let's find it out. Why do we think it's what we think it is? What?
I think it's infinite because the last row.
What? As the one. So let's think about this. Like, matrices are just like arrays of numbers. What does that last row say? Essentially 0 equals 1, because how many variables are in this system implied by this matrix? 4. And the fifth column is always like the constants on the right-hand side of the equals. So essentially this bottom row says 0 equals 1, which means what? This is inconsistent. 0. Inconsistent. So what change could I make so this had an infinite number of solutions? I think you said the opposite of what you meant. 0 over the last one is, yeah. So for what values of x and y is 0 equal to 1? None of them, right? But for 0 to equal 0, that's true. So this one's inconsistent. What about this one? This one has a solution. A unique one or like a bunch of solutions? Okay. So let's say that this thing is, let's say the variables are w, x, y, and z. Do I know what z is? 5. And then could you get what y is? I think it has to be 0. Or wait. -5, sorry. I got them flipped. But yeah, so you can kind of do what we did yesterday and kind of backfill all your variables, right? And that really comes from this, the fact that we were able to write this in row echelon form and get this upper triangular form. Those are basically equivalent. Like you're only going to get that upper triangular form if you have a unique solution. How are we doing? And what about this thing? Okay. What tells you infinite number of solutions? All zeros in the bottom. So when we have infinitely many solutions, we can still, let's try to be specific as we can. So again, our variables are w, x, y, and z. Let's end by ironing this out. What can we say about our solutions? Something equals 1. C equals 1. Which means what else? So we know z equals 1. What does this next equation up say? X minus 2y equals -4. And the top equation says x plus 5z. No. Plus 3z equals 3, right? Or plus 3 equals 3. So I think I have that. So I have a couple parameters here. I think W equals negative 5y. And then X equals 2y minus 4. Z is the only one we like. The Z equals 1. That's locked in. That has to be true. W, X, and Y are all governed. So basically, what controls the rest of the solution? At least the way that I've written it. Y. You can choose whatever Y is, but then W and X get the W and X depends on whatever value of Y you choose. So infinitely many solutions, but that's as specific as I can get about it. All right, I have kept you 1 minute over. I will see y'all next week. Please come back to class with the same number of fingers you have.